This is Jed Deame talking about military-grade security for video over IP. This is an encore presentation, fascinating the lengths to which you can go to really protect your streams if you're interested in it. So stay tuned for a great talk from Jed. Thanks.
Okay, thanks, Wes. Hello, everybody. Thanks for coming out today. As you mentioned, I'm Jed from Nextera. We're providers of IP cores for 2110 and NMOS. We also do quite a bit of work on security. And I'm here today to tell you about what we've been up to and kind of give you a primer on security, teach you a little bit about what we've been working on, what we've learned, and how to protect your content. So the agenda is we'll first talk about why do we care about securing video over IP. Then I'll go into some details about how the different types of security work, different keying systems. We'll talk in some detail about NMOS security, which is one of the newest components of the NMOS suite. And then we'll do a customer use case at the very end. So why secure video over IP? Well, we have high value content. We want to protect it, right? Doesn't matter what it is, whether it's military content or whether it's broadcast content, it's worth protecting. We want to keep any unauthorized streams off air. That's crucial. One thing we have to realize is there are hackers everywhere, and more we're realizing the threats are inside the facility, even more so than outside. So there's three classes of protection that I'd like to talk about today. The first is essence encryption, which it hasn't got a lot of attention so far. This is actually taking the content and encrypting it so that unauthorized people couldn't see it if it accidentally got routed the wrong place. And then we'll talk about control encryption, which is a little more common, to make sure that the routing is authorized. And then a little bit about environmental protection. So one of the important things to look at for security is the cryptographic elements itself. And turns out the US government's done quite a bit of work in this, and they've published some specs. One is called FIPS 140-2, and the other is called NSA Suite B. So we'll jump into those first in some detail. So this is actually the document called FIPS 142. It was published by the National Institute of Science and Technology, and it's got quite a bit of detail. Even back 2002 and earlier, the government has had to deal with these problems. So there's a lot we can do to leverage the work that has been done by NIST and these government agencies. One important point I'd like to make is on the distinction between ports and interfaces. An interface could be a data or a control interface, but a port is more of a logical interface. So one of the things that's important is that you don't necessarily have to have separate interfaces physically. You can actually protect your content and protect your systems by logically separating the ports, and I'll discuss how to do that. So the FIPS 140-2 system specifies a number of levels, assurance levels, they call them, 1 through 4. I'll go through those kind of in detail. Security level 1 is the lowest. This is for physically protected environments where you're not worried about a third party getting to it. And really the requirements are pretty simple. So this is something I think everybody could take advantage of in this video over IP space. You just need some kind of approved cryptographic algorithm, and I'll talk about those. Any compute platform is fine. You don't need any special approval or validation of the operating system or the computer platform, and no physical security is required. So really just saying use some kind of cryptographic system, whether it's in the control, whether it's in the data, however you can to try to provide that first level of protection. Security level 2 takes it a step further. In addition to the ones we talked about, now they require that you have a trusted operating system. And what does that mean? Well, there's this common criteria evaluation assurance level that's provided in this FIPS 140. And what they do is they publish these protection profiles. They give you guidelines for your operating system that say you must turn off these ports and you must make sure that you're protected at this certain level. And again, this applies to anything we do in this industry and other industries. It's important to make sure that any computer systems are protected as much as possible from hackers. Tamper evidence is also nice. For level 2, you really just need some kind of security sticker or tape or something, so if someone opens up the box, you can see it, you can tell that it's been tampered with. And also some kind of authentication. You need to log in. It's not, they don't require individual identity-based, it could also be role-based. So it's a little bit loose from that standpoint, but still better than nothing, right? Security level 3 is really where they step up their game. It says, okay, not only am I going to be approved cryptographic algorithms, but I'm going to use encrypted keys. And we'll talk in a minute about how the keys work with the algorithm. Higher level of OS validation, higher level protection profiles, and also tamper response. So not just did someone open my box, but detect that someone opened my box and zero out all the data. Right, so this, this is again for military level, and maybe even for some broadcast facilities, you would need this. No more role-based authentication. It must be, this is me, this is my name. Maybe it's even done with some kind of electronic ID, a CAT card or something like that. And any plain text keys must be set on separate ports. I talked about ports in the beginning. Just make sure if you're typing in a password, it can't be lifted off by someone. Level 4 is really for the highest level where you need unprotected environments. I've got some kind of box, I've got a gateway that needs to be out in the open, and I can't be there to keep my eye on it. So further step of validation on the operating system, and also protecting against things like voltage and temperature extremes, because those are some techniques that hackers can use. They can apply heat, they can alter the voltage that might break some of your protection systems. So for the PowerPoint that's online, I've got all the details of 140-2. I won't go through this eye chart, but you can see there's a little bit more detail than what I summarized. There's also another standard called NSA Suite B, and the NSA has actually spent quite a bit of time looking at the big picture of all the different types of systems that need to be specified in a secure environment for things like key establishment and digital signatures and integrity. There's a lot of buzzwords, a lot of alphabet soup that's really difficult to understand at first glance. So I'm going to spend about 10 minutes going through each of these so that when you see these in the future, you'll know what they mean. So this is a security primer. We'll jump into the first one. Encryption, you've probably heard of AES, Advanced Encryption Standard. It's a symmetric key algorithm, which means the same key that's used to encrypt the data is also used to decrypt it. That kind of makes sense. They've got different block sizes from 128 up to 256 bit. And really, the goal of a cipher like AES is to take plain text and turn it into ciphertext. Could be text, could actually be video, could be audio, could be anything, but something you can understand into something you can't understand. And the way it does it is by doing these transformations of the data. And if it's AES 256, it's actually transforming it 14 different times, mixing it up, stirring up the bits in a prescribed way that prevents unauthorized access. There's a couple different modes, CTR, which is counter mode, Galloy counter mode, and it's been adopted and used by the government worldwide for many years. If you want details on it, it's in this other NIST publication, 197. So now that we've got a way to encrypt our data, we need to see, well, how strong is it? And a lot of people ask, well, I should just be able to hack this. I can just try every combination like you do on your luggage. If you forget your combination, in about 10 minutes you can try every combination. Well, how long would it take with AES if I wanted to do it? Well, in the AES 128, which by the way is what's used in the HDCP standard, it would take 2 to the power of 128 bit flips. That seems like a reasonable number. Well, is that really feasible? Well, it turns out the energy required to do this on a standard compute platform is about 10 to the 18 joules, which is about equivalent to assuming 30 gigawatts of power for 1 year. Not so easy. Ends up being about 1% of the world's energy production. So maybe not so practical to guess it, but okay, you want some more power? Maybe you say, well, I've got a specialized computer. I'm not just using a PC. I've got GPUs, or I've built a chip to do this. Well, that's why they came out with AES 256, to really take it to the next level. So what would it take to crack AES 256? Well, if you could invent a supercomputer Doesn't exist now. If you could, they could check a billion keys per second, then it would take about 3 times 10 to the 51 years to try every possibility. So I think we're safe with this one. So, okay, so we talked about encryption. There's also key establishment. There's 3 different ways to do key establishment. So this is the key that encrypts the data and also decrypts the data. Where does that come from? Well, there's 3 ways to do it. You can use public key encryption, you can use digital signatures, or you can use this PKI, public key infrastructure, which is what's used in the NMOS system I'll talk about in a minute. So let's go through a couple examples of these so that they're a little bit easier to understand. Public key encryption. So let's say we've got 2 people that want to communicate. Let's say Bob and Alice have got a little inner office fling and they want to send their love notes back and forth, but they don't want anybody else to see them. So Alice can actually generate a set of keys, a public key and a private key. She gives her public key to Bob. Bob can then type an email message, for instance, encrypt it with her public key. It turns it into some non-readable text, and then she's the only one that can read it because she has her private key. This private key decrypts the data from this message. Advantages, it's simple and effective, but the big disadvantage is it's subject to man-in-the-middle attacks. What does that mean, man-in-the-middle? Well, somehow Alice has to give her public key to Bob. Maybe she writes it on a piece of paper, maybe she emails it to him. Well, it turns out Bob's ex-girlfriend is an IT hacker. She could intercept this key and put her key in place. So now every message that Bob sends is encrypted to his ex-girlfriend's public key. So then she can see what's going on. So not the best approach. So how do we solve the problem of knowing who sent me a message? Right? You get emails all the time, maybe from people that maybe it looks like someone in your company, but it actually isn't. I've seen a few instances where it looks like a CEO sent an email to a subordinate to do something, to pay a bill, and it wasn't legitimate. So digital signatures is a way to mathematically verify the authenticity of a message. So in this case, Alice would send her private key, she would use her private key to sign a message. This isn't encryption, this is just a signing process that alters the data based on her key, so that when Bob receives it, he now knows that message must have come from Alice, because I'm validating it with her public key. So that solves one of the problems of how do we make sure we know who has sent the data and where it's come from. So there's a couple other different types of key exchange mechanisms we can use. The next one's called a Diffie-Hellman key exchange. This is a very elaborate mechanism that allows you to move a key from point A to point B in a protected, encrypted way. So the typical way to move a key, you could have a trusted courier. You could have someone maybe mail a key to someone in another location. You could write it down on a piece of paper and hand it to them, but that's not really great. What if there was a way where either side never had to share a key, if they could come up with a shared key between the 2 of them? So here's an example of this, Diffie-Hellman. So we got our friends Alice and Bob again, and they want to send a secure message. Each of them comes up with their own private key. In this example, I'm just using 5 and 4. Normally it would be a much larger number, but this works too. And they agree on 2 things. They agree on a prime number, and they agree on this generator of P. So they agree on 13 and 6, let's say. You do a little bit of simple math on either side. So Alice takes her key and does a power 5 mod 13 and some other math and comes up with a number 2. And she sends that key over to Bob. So she's not sending her 5, she's sending a mathematical modified version of it with some publicly agreed numbers. These are all in the clear. Bob does the same thing on his side. He does some math to his key and generates a number. He gets a 9, he sends this over here. One more math step, they actually end up with a shared secret key. It's actually a very clever algorithm. By never sharing their private keys, they both end up with the same answer. So now you've got this mechanism where 2 parties that all they have to do is agree on a couple numbers in the clear, anybody can see these, they can end up with the same key and send messages back and forth. So the third way to do this is called a public key infrastructure. So this involves a third party. This says, I want to be able to authenticate keys with a key authentication service, and I also want to be able to create and manage and even do things like revoke keys. So this is what we use in the NMOS system. So it's a much more powerful system that gives us a lot more flexibility. So in the case of NMOS, we'll walk through how that actually works. So you've got your typical broadcast controller. You may have an IP source and an IP destination, just like in a typical NMOS environment. We've added a couple new pieces though. We've added an authentication server. So what we do here is the broadcast controller, instead of just sending a switch command, first it sends a command to the authentication server using OAuth. And it authenticates itself. It says, this is my identity, I've logged into this as a user, please authenticate me and send me a token that says, yes, you're cleared to make a switch command. Once the broadcast controller, which it could be a button panel like we have over here, once it gets this token, a user maybe selects route source 1 to destination 2. Those commands are now sent along with this token, this JWT token, to the source. The source then validates this with the public key of the authentication server. It says, okay, that is a valid key. I'm authorized now to start sending this flow. Then the broadcast controller sends a command to the destination, which then is authenticated with the same public key, and then the flow can move from source to destination. So a little bit of extra effort, one extra piece of software running on a server somewhere. Now we're in control of our routing, right? This is something that we even didn't have in the SDI world. We can now make sure that someone has logged in and they're authorized to actually do this route, so you're not sending something on air that you're not supposed to, or not sending content someplace where it doesn't belong. This specification is called BCP 003. It hasn't been given an IS number yet, it will soon. We've got a demonstration of this actually on the back side of that wall over there. So some of the core technologies that are used to make this happen, we talked about PKI, this public key infrastructure, HTTPS, which is essentially HTTP over TLS, which is a connection security mechanism. And this is what the authentication server does. It says, yes, I'm sending an HTTP request, but I've validated that it's a proper endpoint. Another technology that's used is REST, representational state transfer. That's essentially using HTTPS for very simple commands, put and get. It all sounds really high tech, but a REST API is nothing more than using HTTP to send simple put and get commands. But they're authenticated with this secure interface. We're using JSON technologies, JavaScript object notation. Again, sounds really fancy, but it's just a combination of key value pairs. Resolution, 1080p, very simple. And then on the security side, we use OAuth 2.0 and JWT. I won't go into too much detail on those, but you saw on the previous slide how those work. Requests for authentication, and the JWT, the JSON web token, is what authenticates you to do the switch. So what are the goals in NMOS for security? Well, it's important to have confidentiality. We want to make sure that we know that the data moving back and forth is unreadable by a third party, so someone can't get in the middle and take over control. Identification. We want to make sure that the API that we're interacting with is trusted. This is part of the digital signature piece that we talked about earlier. We want to make sure we have integrity of the data. It's not tampered with from point A to point B. So if a man in the middle tries to jump in and do a switch, if he doesn't have that JWT token, he's not allowed. The switch isn't going to go anywhere. And authentication. Someone's actually got to log in and make sure that they're approved to work in this environment. So there are a few different cipher suites that are approved in NMOS. And maybe before this presentation, this would have looked like a bunch of alphabet soup to you, but hopefully afterwards you've got your Johnny Quest decoder ring, so now you can see what these things really mean. TLS is Transport Layer Security, which is HTTPS. EDCHE, a Diffie Hellman key exchange, that was Bob and Alice exchanging their secret information in a way where they could have a key without sending it in the clear. AES encryption of the different modes, secure hash algorithms, and the counter modes with the block cipher. For NMOS, this is the minimum requirement here, AES 128, similar to HDCP, but if you have very secure content, you might want to go as high as AES 256. So here's an example of a customer case study. So how does this all actually come together in the real world? How would we use this in a facility? This is a customer we worked with named Pesa. It's been in the business for many years. They set off to build a secure KVM system, KVM meaning a keyboard video mouse extension system. And we worked closely with them to develop a high level of security around this. So in this example, we've got a bunch of servers that are back in the machine room. These are your PC workstations. So the idea is instead of having the workstations out in the control room, you put the hardware in the back, and then you have your operators up in the front, maybe in a main control room. Maybe it's got a large video screen that's shared. And they're able to remotely connect, any operator can remotely connect to any computer. So if you've got a similar problem, you want to protect that. You want to make sure that that the operator has been authenticated, right? So that's step one. Implement some set of user authentication. Could be type in a password, or it could be swiping a CAT card or something like that, some kind of electronic login. The next level of security that was implemented was the encryption of the video. So this is something that hasn't been done much in the broadcast space, but in a military command and control environment, it's crucial. So all the HDMI streams that are coming out of these servers are actually encrypted with a very high level of security and a proprietary key exchange between these systems to ensure that the data going from server A to client B can't be accessed by an unauthorized client down here. And then the last piece is a secure control system to make sure when the routing is done, it's actually done with an authenticated user and using HTTPS. You could have a remote monitor in this system, by the way, someone in another facility monitoring it, and you could even bring in SDI sources, so a pretty clever system. In summary, security is important. We have content that we need to protect. There are many ways to protect it. We can protect it by protecting the control system, making sure that only authenticated users can do switches, and we can encrypt the video from point A to point B so that unauthorized people can't intercept it. The government has spent a lot of time and energy developing these standards like the FIPS 140 that I talked about. So I recommend that you look in that a little bit more closely. And if you're specifying equipment, maybe ask what type of security measures have been installed in the equipment. And this technology is readily available, and it works with 2110, 2022, et cetera. So if you'd like to see some of this stuff in action, you can come join us either at the Nextera booth or the Pesa booth. We're both in the South Hall, 10-230. And if you have any questions, I'd be happy to entertain them.
Okay, thanks, Jed. Any questions? So where do you see this going? Do you see lots more people doing secure installations like this?
Yeah, we've seen a lot of requests from the large television broadcasters, content owners, anybody that's got something of value that they want to prevent from getting out there. There have been initial requests for control security. We want to make sure if someone's logged into their router, they know who it is, they know what they've done, and they're not doing anything they're not supposed to do. So the move to IP creates a lot of value for customers, but it also creates opportunities for hackers. So we have to be really careful that with this new capability, we provide the level of protection that's required.
All right, thank you very much, Ted.
Thanks.